rotate instructions. Rotate to the right, rotate to the left, RR and RL, and rotate to the right with carry and rotate to the left with carry, RRC and RLC. We'll see a program. Here we are considering a program to transfer the value 41H serially, that is 1 bit at a time, via pin P21 port. P2 is the port 2 and the pin is P21. So we are going to transfer the data through the pin P21 bit by bit, and serial data transmission, and to show that it is the start of the data and the end of the data, we are putting two highs, that is 1 1 at the start of the data and 1 1 at the end of the data. So before transferring the 8-bit data, the first we have to make P21 as 1, then again 1, then we'll transfer the data, and after transferring the data through P21, 8 bits through P21, last again P21 will be made 1, then again 1. So that is start of the data and the end of the data. We are putting two highs and send the LSB first. So send the LSB first means we are going to rotate to the right. Yes, you can imagine it like you have the data stored in a register. Like when we are rotating through rotating the accumulator contents. So it's always the accumulator contents. So you should have the data in the accumulator, and you must pass the data to P21, and the first value in P21 should be 1, second value should be 1. Then you should have the data, 8-bit data, bit by bit, sent to P21 with the LSB first. And after transferring the 8-bit of data and also the first 1 1, you have to transfer 1 1 again to show that the data has ended. So in total, P21 will carry 8 plus 2 plus 2. That is 12 bits of data will go through P21 bit by bit, 1 bit at a time. Okay. So what is the data that you are going to transfer through P21? It is 41H. Okay, so 41H, if you have to transfer through P21, you have to rotate it as we told. So in order to rotate it, you have to store the data in the accumulator. So the accumulator will have the content 41H. So here we have the accumulator content as 41H. Then the first bit that you want to send through P21 is 1. So for that you can set the bit in P21. Again you want to send a 1. So again you can set the bit. So two set bits P21. And after that you can rotate it to the right, because we are transferring the LSB first. You'll rotate to the right. So accumulator directly you can't rotate transfer to P21 bit by bit. So you'll be transferring it through the carry to the P21. So this here accumulator has 41H. So 0100 0001. that will be there in accumulator. Set B P21, set B P21 will send the start of the data, two ones, two highs at the start of the data, and this is just a counter to show that the 8 bits of data has been transferred. Okay, so why are we going for RRC and not RR? Because in order to transfer the bits through P21 from accumulator, you can do it through the carry only. Because it is bit by bit you need to transfer. Serially you have to transfer. Only one bit at a time. So accumulator contents you can transfer only 8 bits at a time. So you just want one bit at a time. So for that you will be transferring the each bit to the carry from the accumulator, and from the carry to the P21. So RRC accumulator means the first bit, that is the LSB bit of the accumulator, will be transferred to the carry, and then move P21 comma C means that value, the LSB will be moved to P21. So the first bit of the data, that is the LSB of the accumulator content, that is 41 hash. So it is 1. Okay, so that will be transferred to the P21. Then you'll continue doing this until the 8 bits of data has been transferred. So that is why you are giving DJNZ R5 here. Okay, so it is not here, it is again. Okay, this is wrong. It is not here, it is again. Okay, so after that, after transferring the data, you need to again show that it is the end of the data. So for that set bit again you have to put, because you need two ones at the end of the data. So that is why again you set bit P21. So here you have 41. Here you have 41. Then when you rotate it once, the first bit will go to carry. Then you will move the carry to P21. Again that is continued. So the next bit will go to carry, then to P21. So this will continue until all the 8 bits has been transferred to P21. Okay. So after that P21 will be again set to 1 twice, so that we know that all the 8 bits of the data has been transferred. So that is one example. So another is write a program to bring in a byte of data serially 1 bit at a time via P27 and save it in register R2. The byte comes in with the LSB first. So here, what is the difference between the two programs? In the first program, you already have the data, and that data should be moved to P21. In the second case, you are bringing in the byte of data serially 1 bit at a time via P27. So P27 is acting as the input in this case, and in the other case the P27 is getting the data from the accumulator. Here P27 is giving the data to the accumulator, and finally whatever data is there in the accumulator. Why accumulator? Because the rotate operation can be done only through the accumulator. So finally the accumulator will get the all the 8 bits of data, and that data, that 8 bits should be transferred to the register R2. Okay, so again we have uh, since it's 8 bits of data, we are setting a counter R5 to 8, and I'll just show you how it is. So it is P27 um, carry, then the register. So this is the setup. So it is P27, then carry, then the register. So P27 will have the first bit of data that will be moved to carry, and through the carry to the accumulator. Okay. So for that, move P27 to C. Then rotate to the right with carry the accumulator. Then this is continued until the 8 bits of data has been transferred. So after transferring the 8 bits of data, the accumulator has the 8 bits of data that is moved to R2, because you want, in the question you need to save it in R2, right? So these are similar programs. You can check them out in the PDF or in the textbook. Now next instruction is swap. So what swap does is, see, 8 bits of data, 1 byte of data, you can consider it as 2 nibbles. So 2 nibbles means the higher order nibble and the lower order nibble. Higher order 4 bits and the lower order 4 bits. So this is D7 to D4, and this 4 bits is D3 to D0. So if you want to interchange this, that is swap, you want to suppose the question is like in the earlier case 41H. If you want to change it to 14H, 14H. Okay, 41 is made to 14. 41 is made to 14. So you are swapping the nibbles. So for that you need an instruction called the swap. So swap is also done on the accumulator. So before, after, this is what happens if you write swap A. So here you can see that find the contents of register A in the following code. So in A part, move A comma 72H. So A gets the value 72H. So that is A will have 0, 1, 1, 1, 0, 0, 1, 0. So that is what the content of accumulator will be. And next instruction is swap A. So when you give swap A, what happens? It will change to 27H. Now the B part is, suppose you don't have a swap instruction. What happens? Okay, but you need the same output. Okay, so you don't have the swap, but you want to swap. Swap instruction as such you don't have, but you want to swap the nibbles. So how do you do that? Using rotate to the left. Now here again there is a mistake here. They've written the rotate to the left, but here rotate operation is not done. So that's also a mistake. You can do and see. We'll see in HSIM this particular we will explain at that point in time. So that is swap. So the same program, let's see. So move a comma 7 to h. So this is what a has, 7 and 2. So rotate to the left a. So what happens? Rotate to the left a. So rotate to the left means each bit will move to the left and d7 will come to d0. So what happens? It will be 1 1 1 0 0 1 0, and the LSB will be the MSB. MSB will move to the LSB. Again rotate to the left, so that will be 1 1 0 0 1 0 0, and MSB will move to the LSB. So still it is not 27, so we will see how many times it should be rotated. Again rotate, so that will be 1 0 0 1 and 0 0 1. MSB will move to the LSB. Again not 27, so again rotate 0 0 1 0, and that will be 0 1 1, and MSB will move to the LSB. So now it is 27. So since you have 8 bits, you want to swap the nibbles, and nibble has 4 bits. You are rotating it 4 times. Okay, so that the same process of swapping happens here also. So we'll just if we run it, you can see what should you look at. Accumulator, you must look at the accumulator. So accumulator, if you see, it will be 72 first, then it will be what is this, 1110, so that is E4. Okay, that is E4. Here this is 12, so C9, this is 9 3, and this is 27 2 7. So this is what you should get in the accumulator in each step. So let's see. So you can see the accumulator. So finally you have got 27. So if you want to delay the process, like if you want to actually see what's happening, if you're getting all these values, then you can just put a delay in between. Okay, so it's just a call delay like we used to do, and you can just some value origin 300h, and the delay program here. So move to some register counter some value. I'm just putting it as say 10, decimal 10. Then we'll just increment the counter R0, so that unless and until it becomes equal to 0, so much delay you're getting. So djnz R0 comma L1, and after that you'll return to the original program. You can put this For better understanding, you can put it after every. You don't need this in theory as such. You just, if it's a program you want to show it properly in a lab, then you can do like this. Okay. So you can see the accumulator 72, E4, C9, 93, 27. So you can see it in a better fashion if you put the delay. In the theory exam, or if you're just writing the theory, you don't need to complicate the program by putting the delay and all. No need of that, just the program is enough. Okay. ASCII and BCD code. So here 0 is equivalent to 30 in ASCII. So if you convert that to binary, that will be 3 and 0. BCD, you have two types, packed and unpacked. BCD unpacked equivalent to 30 in ASCII is 0. Or you can say that key is 0, so this is 0. This is 1 means BCD is 0, 1. Likewise, 9 means it is 0, 9. So ASCII, you add a 30 to this. So that is the relation between ASCII and unpacked BCD. Okay. So here in this case, in microcontrollers, it has a real-time clock and it provides the time of the day, that is hour, minute, second, date, year, month, day, continuously regardless of whether the power is on or off. But this data is provided in the packed BCD form. Okay, so in order to display that in the LCD, it must be in the ASCII format. So what you should do is convert the packed BCD to ASCII format. So packed BCD, suppose it is 29H, then the unpacked BCD will be 02 and 09. 02 and 09. So that when you pack it, it becomes 29. Okay, 02 and 09. When you pack it, it becomes 29. And if it is ASCII, then that will be 32 and 39. So that is the relation between ASCII packed BCD and unpacked BCD. So for LCD display, you will need these. So to convert ASCII to packed BCD, so the key is say 4, then ASCII is 34. So unpacked will be 4 and 7, it is 37 and that will be 7. So when you pack it, you need 47. That is 4 from here and 7 from here. So that is this. Okay. So if you want to convert 47 in packed BCD form, what you do is you take the input as ASCII, unpack it, and then make it packed BCD. So how do you do this? So there is a mistake in this particular program. Syntax errors are there in this particular program. So you have to note that this is not correct, because here you can see that ANL R1, 0F. This is not a valid code. So the entire thing will not work because ANL will, the destination should always be accumulator. So this is wrong. We'll do that in ASCII. So here, if you see, we've written that program, corrected that program. So first I'm giving 4 to the accumulator, 7 to R1 a register. Then I'm masking. That is when I see when you write 4 in quotes, that means that it is in the ASCII format. So A will actually have the value 3, 4. That is 0, 0, 1, 1, 0, 1, 0, 0. So if you put this quotes, that means that it is in the ASCII format. So after the first step, the accumulator will have 34 H and R1 will have 37 H and ANL A comma 0 FH. So we know that when you AND using 0, then what happens? That particular nibble will become 0. So you're masking the higher order, that is 34. 3 you're masking. You don't want that 3. And in 37 also you don't want that 3. Okay. So in order to mask that unwanted higher order nibble, you'll be ANDing it with 0f. Okay. So when you AND with 0f, what happens is, yeah, from 34 you get 04, and then you're swapping A. Swapping A means it becomes 40. Okay, so what you want is, you want it to be 47. Okay, so you're taking 34, 37, masking the higher order nibble, making it 04, then swapping it to make it 40. So here it becomes A equal to 40H. Okay, so again I want to do the same thing with the 7. So, and I can do it only using the accumulator. So that was the problem in the earlier PDF. So for that, I'm just going to store this 40 in a particular register. So I'm just moving it to R0, keeping it safe there, and then going and taking 37, and I'm going to operate on that. So again, I'm masking. So I'm getting 07 here, and that 07 I'm moving to some other register R2. So now you have 40 in R0 and 7 in R2. Okay. So next, if you OR it, OR the 40 and 7, then you'll get the 47. So for that, I need to get this R0 value into the accumulator, because OR operation also the destination should be the accumulator. So I'm ORing 40 and 7 to make it 47. So we'll do this step by step and see. Here, see, if I do the first step, means each step by step, you can see the result. So first step, now everything is 0, accumulator is 0, R1, okay, reset, and okay. So first accumulator is 34. Second step, R1 becomes 37. Third step, I want 04. So accumulator becomes 04. Next step, I'm going to swap A. So accumulator should become 40. Then I'm moving that accumulator value 40 to R0. Yes. Then I'm moving the 37 to the accumulator. Then masking it. So I get 07. Then I'm moving that 07 to another register R2. Then I'm moving the R0 to the accumulator. So accumulator gets 40. Last step, or A and R2, so I get 47 in the accumulator. So that is